To stay on time?
Yes, go ahead.
Okay, let me start. Yeah, the key slides are later, so people trickle in, they'll still won't miss the key point. So I'm going to be talking about a project that we've had lots of different funders and supporters on this project. We started in 2015, and I'm working with Shara Armstrong, who will be giving a talk after me in the other side. Ranasan Seyon, who's a modeler, and William Perry, who is our helps immensely with all of our data management, data analysis. So I'm really a hydrogeologist and a water quality specialist. So what we're trying to do in our project is try to figure out how easy is it for someone to actually improve nutrient losses and surface water quality. So we're basically just trying to try a cover crop application without actually changing a lot about the management practices, without controlling what the farmers are doing on the landscape. We're really just adding cover crops. And of course our goal is to see if this will be an effective contribution to the goals of the Illinois Nutrient Loss Reduction Strategy, trying to retain nutrients on the landscape and improve surface water quality. So there have been some studies a little bit like this in the past in our general area of central Illinois. This is a long-term study in Mackinac River watershed area where they put in a lot of different best management practices into one tile drain watershed, and they put no best management practices into the other one. And you guys can tell me if you see any difference between the black and the white dots. Any changes over the long term? No, right? So in this particular case, even when they put in all these grass buffer strips and things like that, the water quality coming out of those watersheds totally didn't change at all. So some of the things that have traditionally been used for best management practices in agriculture just aren't effective in tile drain landscapes, because that tile just takes all the water right from under these waterways and things like that and puts it right out into the stream. So that's kind of where this idea of large-scale cover cropping came from. We're doing that to be a best management practice that might be more effective. So we're working in the Lake Bloomington watershed. We call this a paired watershed study because we have one watershed where we're not doing anything at all. We're just measuring the water coming out of that watershed. And then we have another watershed where all we're doing is adding cover crops. And we're just not even cover cropping the whole watershed, actually. We're only cover cropping 60% of the watershed. And we, the farmers, they control everything else. What they plant, when they plant, how much fertilizer they put on, anything else that they want to do. So we started our first cover cropping in, actually I think it was fall 2015. So here's a map of our site. This is where we are in McLean County, central Illinois. This is Lake Bloomington here, which is regularly exceeds nitrate concentrations. It's a drinking water reservoir, so it's exceeding EPA limits on an annual basis at least. So it's a good watershed for us to be doing some of this work in. This is our reference watershed up here, and our sampling location. All the tiles drain out to this outflow point. And this is our treatment watershed down here. And the gray hashed areas represent the fields that we apply the cover crop in. So in this sampling point here is our pour point, our outflow point. There's a tile here that we're measuring the water quality from. There's really no surface water flow in any of these watersheds. It's all subsurface tile. Here's what one of our sites looks like, the reference site. This is a soybean year. This tile here is sort of draining this back part of the field here, and this tile here is draining off the fields off to this side. And we are collecting water from each of those tiles, like on a flow basis. So basically, as often as every 15 minutes during a storm event. Our other our treatment site where we apply the cover crops is actually behind this road back here. But this is a 24-inch tile main that's draining that whole 700-acre watershed. And here's our instrumentation unit, so we're sipping up water coming out of this 24-inch tile. We apply the cover crops aerially because you can't easily drill in for such a large amount of area. And also we're trying to not disrupt the farmers as much as possible. So on this map here, these lines actually represent the flight paths from the cover crop application in 2015, where red is the cereal rye radish combo and yellow is the oat radish combo. And all of these farmers are in a soy corn rotation, so every year this is just flipping from one to the other. So and we've had pretty good success with the aerial application, although some of you probably know cover crops can be really variable, and in this case especially we're very weather dependent. It depends upon if the stands, how soon the stands come down, how much light the seedlings get, and how well that growth is. So those cover crop growth can really vary depending upon the conditions at when the planting occurs. And so we do monitor that too, right? So here's a fall 2016. It was a great year. We had a lot of rain. The students who worked on the project all called it our rural beautification project because it was just so green in these watersheds, in these fields where we cover cropped. But other years you don't have as good a growth. And so what we do every fall is go out in spring and sample at these points. So we're not getting high resolution sampling, but we're getting out to each multiple places in the fields and taking some cover crop samples. And we can take those samples and we do two things with them. We measure the biomass, how much above ground cover crop biomass is there, and how much nitrogen is there in that biomass. So here, for example, you can see in a really good cover crop year, fall 2016, we had quite a lot of pounds per acre compared to a cover crop year where we just didn't get as good growth, and we only had up to 900 pounds per acre. So in the map right here, the greener it is, the greater the biomass is. And as you might expect, where you have more cover crop biomass, that's also where you have more nitrogen uptake by that cover crop. So obviously when that gets terminated in the spring, eventually that nitrogen will become available again for subsequent crops. So we're getting, if you apply oats radish in this year where we had a good cover crop, 21 pounds of nitrogen per acre taken up, and for the oat radish, and for the cereal rye radish, 58 pounds per acre. And that difference, which is pretty big, right? It's twice as much more, is really because the cereal rye grows again in the spring. So we have a little bit more growth in the spring, more time to accumulate the biomass and the nitrogen uptake. And that's why parts of this are green and parts of this are red. These are the places where the cover crop is not winter hardy. Because we're sampling at a really low resolution and we're seeing a lot of spatial variation in the cover crop, we're also exploring some new tools that might be useful. For example, using remote sensing or maybe eventually drone technology. But if we take the samples that we have actually gone and collected by hand and we compare them to metrics that are available through satellite imagery, we can create these relationships between the cover crop biomass and the satellite imagery. And because the satellite imagery is available at much lower resolution, we can then create these high resolution maps of what the cover crop biomass probably is. And so this will help us maybe later in understanding variations in yield or hot spots where more nitrogen is being retained, or places that are maybe driving some of the improvements in surface water quality. We are also doing soil data. So this is, there's two sort of maps here. There's a soil in spring of 2016 and soil in spring of 2018. And you can see that there's a pretty big difference here in basically the colors, the distribution of the colors, right? And so this does have to do with the cover crop growth to some extent. Where you have more cover crop biomass, you see it's negatively correlated with soil nitrogen. So that's because that nitrogen, instead of being in the soil, now it's up in that cover crop. In the long run, because we've been doing this study for several years now, we haven't seen any long-term trends in soil nitrogen, but that's probably also because we have this farmer application going on, right? And so right now what the cover crop is doing is probably overridden by the regular nitrogen management strategies that the farmers are using themselves. So let's talk about the water, which is really the key to a lot of what we're doing. I wanted to show you these graphs just so you kind of see what some of our data looks like. But there's three graphs here. On the bottom is just rainfall. The red is our reference site. The blue is our treatment site. In the middle is discharge. So this is how much water is coming out of those watersheds. You can see in the beginning, the blue, which is our reference site, has more water coming out of it than the red. The blue, which is our treatment site, has more water coming out of it than the red, which is the reference site. And that should make sense because the treatment watershed is bigger. And so the bigger a watershed is, the more water is going to come out of it. But you'll notice that as we go in over time, what you end up seeing is that there's less and less water coming out of that treatment site. And now it's like there's about as much water coming out of the treatment site as there is out of the reference site. And that, of course, is going to have implications for how much nitrogen is coming out in that water. So in the beginning of our project, you can see the nitrogen loads are pretty high coming out of the treatment site, the blue. But by the end of where we are now, you're seeing that however much nitrogen is coming out of that site kind of matches the amount of nitrogen coming out of the reference site. So what this just tells us broadly looking at these data is that there have been some changes in time with our treatment, with our cover crop application. You can also see this data is very spiky, and that's because these are storm events, right? And whenever you have a storm event, you have a lot of water coming out of the tile, and you have a lot of nitrogen coming out with that water. So really, there's kind of two key graphs I wanted to walk you through. This is one of them. And what this graph shows is sort of the average amount of nitrogen load coming out of the watershed. In this case right here, for in 2016, it was soy. And you can see in our treatment watershed, we had a lot of nitrogen coming out of that watershed and not very much nitrogen coming out of our reference watershed. We go into the fall, the cover crop period. Now the watershed that does not have cover crop on it has more nitrogen coming out of it than the watershed that does have nitrogen, that does have cover crop on it. We go into corn the following year. The treatment watershed still putting out an awful lot of nitrogen compared to the reference watershed. But now when you get into 2017, 2018, we go back into the cover crop fall period, and now that treatment site that's getting the cover crop, it really doesn't have a lot of nitrogen coming out of it at all. And actually there's quite a bit more nitrogen coming out of that reference watershed, and then that pattern holds true when we move into the actual crop in the following year. So we've moved from a situation where the blue bar is taller than the red bar during the crop period to a situation where the red bar is taller than the blue bar during the crop period. And so what does that tell us? It tells us that things have kind of flipped a little bit. So instead of, and why has that flip occurred? It's probably because of the cover crop. So what's happening now is the cover crop watershed is putting out a lot less nitrogen than it should be if it hadn't have been cover cropped. So this didn't happen the first time we cover cropped, right? The first time we cover cropped, we only saw a small change, a small difference between the watersheds. But we see these big drops occur as you go further into time. Part of the reason for these changes are discharge. We've had a lot of dry, the past few summers have been pretty dry. So you can kind of see here that a similar sort of pattern where basically we're moving from a lot of water coming out of the cover crop watershed to not very much water coming out of the cover crop watershed. So having less water coming out is going to help reduce the amount of nitrogen that's also coming out. A different way to look at this is through these cumulative nitrogen loss curves. So these are only for spring because we found that spring is the time period where you're losing most of those nutrients. Once the soil warms up and we get the spring rains and there's no crops on the field, that's when we see a lot of the nitrogen leaving the fields. And all of our farmers, I think, are fall applying right now. So in 2016, when we first started, here's our cover crop watershed. The cover crop watershed, by the end of the spring, it's put out an awful lot of nitrogen compared to the non-cover crop watershed. That's because this is a bigger watershed, it's got more water coming out of it, so yeah, okay, that's fine. But what we're really looking to do is see, will this line move down, right? That's what we want to see. As we add cover crops over time, will this watershed put less and less nitrogen out? What we would expect for the reference watershed is that it's not really going to change very much over time. It'll be weather dependent a little bit, but this line shouldn't be varying a whole amount. Here's 2017 spring. So now in 2017, you can see that the losses from the treatment watershed, the cover crop watershed, ultimately they're still a bit higher than the reference watershed, but these lines are a lot closer together than they were a year ago. So after 2 years of cover cropping, we're seeing the treatment watershed already look a lot like things have changed in it. And then from this past spring, now the reference watershed is actually putting out much more nitrogen than the cover crop watershed, even though the reference watershed is smaller. So we've almost done a complete flip in how much nitrogen is being lost from this watershed once we started adding cover crops onto it. We have a couple of other steps going on this project, so we have another year that we're going to keep working on this. Most of the farmers that I've talked to have said that you need 6 to 8 years before you get yield increases, so we're starting to do some economic analysis to look at some of that and look at the yield, get some yield data from these farmers that we work with. And we're also developing a model which will take elevation, soil information, land use information, climate information, farm management information, kind of put it all together and create something that then we can use to look at, for example, under certain climate scenarios, dry summer, wet fall type of things, how would we expect things to change? And so this might be helpful for us at understanding the patterns that we'll see in years that we aren't actually going to measure if we never have a really, really wet year during our studies. So we have this model all set up and a generic model ready, so we're ready to start playing around with this a little bit. All right, so to summarize, I guess these are some of our main findings. Basically, you can do large-scale cover cropping, right? Across multiple fields within a watershed in an effective way. We're finding that storm events are what are driving nutrient losses. We found that cover crops can improve surface water quality. Once you start doing it for a few years, you have reduced nitrogen losses. We do have phosphorus data, but that doesn't right now look like we're seeing as much of an impact on phosphorus as we are on nitrogen. And a lot of this seems to be due to just decreased water losses. From our cover crop work, we know that winter hardy cover crops are producing the best results because you have that extra growth in the spring for nitrogen retention, and that seems to be correlated with higher water quality in those years. We also know that this is not a quick fix, not 1 year. It's going to take a couple of years before you start to see these changes come into play. So we're really excited now that we've seen some big impacts in the cover crop watershed to see, is that what we're going to see again this next year? We're going to keep this, if we keep this low nitrogen loss out of this cover crop watershed, we're going to know that this is really effective. So we've only had 2 springs so far where that's happened, so it's such a big change. I still can't believe that that's maybe completely what's going on. So I feel like I need 1 more spring to feel like really confident that this is going to be having this much of an impact. So I think with that, I would be happy to thank all of our many sponsors and collaborators, and if there are any questions, I'd be happy to take them. Because I only had 20